morning. I welcome you all here in my course, Engineering Thermodynamics. Today's my topic is numerical on first law of thermodynamics, part 2. Before I commence further, I should go in detail about what we have covered. So we have seen that basic concept of thermodynamics like system, surroundings, universe, equilibrium, zeroth law of thermodynamics, thermometry, first law of thermodynamics. From their internal energy and enthalpy, we have find out in our previous lectures. Just before that, we have done some 3 numericals on first law of thermodynamics on control mass system. Means closed system we have done, and we are doing in this also we are doing the closed systems or control mass systems we are undertaking. In today's lecture, I am going to cover 3 numericals. That is numerical number 1 related to the first law of thermodynamics of room and computer problem of heat and work transfer. Numerical 2 is related to the first law of thermodynamics for piston and the cylinder problem of heat and work transfer. And numerical number 3 is related to the first law of thermodynamics for room and computer problem of heat and work transfer. So these 3 problems I am going to take in my today's class. All the solutions are abstract. They are not, I am not doing the calculation and all. I am just giving the concept how to solve the problem. So whatever answer, you have to refer the particular steam table or some other equations and all, and then you put the value and calculate yourself. So whatever I am giving, it is just a concept I am giving how to solve the problem. So accordingly, I am going ahead. So here problem, a computer in a closed room of volume 150 meter cube dissipate energy at the rate of 10 kilowatt. The air in the room was at 300 Kelvin, 100 kilopascal. When the air conditioner suddenly stops, what is the air temperature after 15 minutes? So we have to find out the temperature after 15 minutes, how much it is there. So the answer we should get this much. So we will see how to go about. So here we have, we have here the room. This is the room, and here is the computer. So here the only computer is not the boundary, this system. The system is the combination of the computer and the room, and it is shown by this dotted line. This is the system, room and computer as a system as shown in this diagram. So in this problem, the given parameters are V room, the volume of the room is given 150 meter cube. The Q dot, heat transfer per unit time, is 10 kilowatt, or we can write Q into T is 10 kilowatt, where T is the time, and T1 is the temperature which is given at 300 Kelvin. So if we apply the first law of thermodynamics, so we can see that Q12 is equal to U2 minus U1 plus W12. Here W12 is 0 because boundary, there is no change in volume. So this W12 is 0. So now this Q12 is equal to M CV T2 minus T1. So here we know that here P1 V1 or P1 into V room is equal to mR T1. So from here we know that R is equal to 0.287 kilojoule per Kelvin. So here we can find out the mass. Mass is equal to P1 V1 by R T1. T1 is equal to 30, and from here we can get the mass of the system. T1 is given, R is given, P1 is V room is given. So we can get here the mass. Mass we can get from here. So here now Q12 is equal to mCV T2 minus T1. Here we know that T1, we know the mass, we know the C1, we know the Q dot. Okay, so here from here we can find out the T2. So we can find out the final temperature. So this is the final temperature. So here this T2 is equal to Q12 divided by mCV into plus T1. So T1 is given to us 300 degrees Kelvin. Q12 we can, Q dot is given 10 kilowatt. So Q is equal to Q dot into T, 10 into 15 minute into 60. So this is the your kilowatt, and mass we have got, and the CV is constant for the given system. So we got here 370 Kelvin. So by this we can see that is P1 is also given 100 kilopascal. Here P1 is equal to 100 kilopascal. Okay, so from here this P1 is equal to 100 into 15 into M is equal to M into R is equal to 0.287 into T1. T1 is here 300. So we can get here mass. So this mass is equal to 100 into 15 divided by 0.287 into 300. So here we can see that it is 5. So 5 by 0.287. This is the kg. We got this much mass here. This we can take as a here exactly 3. So this will come approximately 0.350. So this is the mass which we have got here, and here this we can put this Q12. So here T2 is equal to Q12 is equal to 10 into 15 into 60. It is the Q plus mass is equal to 5 by 0.287 into CV is given plus T1 is equal to 300. So this we will get here 370 Kelvin. Okay, this is the answer we can find out in this way. Now I will go for the problem number 2, and this problem is related here. I will just read out. A piston cylinder contains 2 kg of air at 27 degrees centigrade, 200 kilopascal. So here the mass is given, T1 is given, and P1 is given. These things are given. The piston is loaded with a linear spring, mass and the atmospheric stops are mounted so that V stop is equal to 3 meter cube, at which point P is equal to 600 kilopascal is required to balance the piston forces. The air is now heated to 1500 Kelvin. So find the final pressure and the volume and the work and the heat transfer. Find the work done on the spring. So on the spring, so this is the system here. So pressure, final pressure and the volume, work done is this, and heat transfer is this. Work done on the spring is 249 kilojoule. So this we have to find out. So this here we will see that this is the cylinder, this is the piston. So this piston is resting on this stop here, and this is the spring here, and here is the atmospheric pressure. So here the system is air. I shown here the system is air, and this you can, I'm putting this dotted line. This is the air. Mass is given 2 kg, so means 2 kg mass is of air is there. So state 1 is given, T1 is equal to 27 degree centigrade, or 27 plus 273, 300 degree Kelvin. Okay, so and pressure P1 is given 200 kilopascal. So from the ideal gas, because this is the air, we can assume air as an ideal gas, So we get V1 from here. We can, here we know the P1, we know the T1, we know the R, we know the M. So V1 is equal to M R T1 by P1. So M is equal to 2, R is 0.287 into T1 is equal to 300 divided by P1 is equal to 200. Itne meter cube. Okay, so this will get this V1 is equal to 0.2861 meter cube. So now here the in problem 2 prime is given, which is the hypothetical states are given to construct the PV diagram. So here V2 prime is given 2 meter cube, P2 prime is given 600 kilopascal. So let us draw the PV diagram. So this you can see here, this is the 1.1, and I am drawing here just dotted line because, and this is your the 2 prime. This is the hypothetical state, so that the slope of this thing can be identified, especially in the spring is a linear. So if spring constant K is not given, that time this type of systems are very useful, and this is used only to find out the slope of the line. So we need to draw the now PV diagram. So here P and this is the V. So state point 1 is given, that is the P1 V1, and here we have to see the system. So we need to draw the PV diagram. The actual state points seems to be in between 1 and 2. It is located on the straight line 1 into prime. So the final is somewhere here in between, and that we have to find out that it is working or not. Okay, so straight line equation, we can see that straight line equation. We know that P2 minus P1. So P2 minus P1 divided by P2 prime minus P1 is equal to V2 minus V1 divided by V2 prime minus V1. Okay, so here what are the, we know this P2 prime V2. So here only this P2 is not known. This we have to find out, P2. So here we have the equation number 1, and here we have the P2V2 is equal to MR T2. So if we solve this 2 equation number 1 here, that is P2 minus P1 by P2 prime minus P1 is equal to V2 minus V1, V2 prime minus V1. So, and here P2 V2 is equal to MR T2. So V2 and P2. So here we will get pressure at the final is 1500 kilopascal. So the solving the equation 1 and 2. So P2 and V2 we get here. We can identify these all problems. So here this work done is equal to, so here if you see P2 prime is 600 kilopascal. So here work done is equal to half P1 plus P2 V2 minus V1. So this work done we will get 367.3 kilojoule. Putting this value P1 plus P2 and V2 minus V1, we will get the value 367.3 kilojoule. Now heat transfer Q12 can be approximate as ideal gas. So here Q12 is equal to M U2 minus U1 plus W12. This du is equal to Cv naught into dt, U2 minus U1 integration of 1 to 2 Cv dt. Here T2 is 1500 degree centigrade, T1 is equal to 300 degree centigrade. So we need to use U2 and U1 by the table as we can use in an ideal gas. So if you put this value Cv T2 minus T1, so we will get Q12 because this we have got. So here this you can see Q12 is equal to M Cv T2 minus T1 plus 367.3. So Cv value we have to put, and T2 1500 minus 300 plus 367.3, and here we have to put the value of the Cv. So we will get the heat transfer Q12 is equal to 2350 kilojoule. So this is our answer. So how much we have got? $367.3 kilojoule, and this minus work done, we can get the work done on the spring 249 kilojoule. So I will go for my third problem, that is the numerical problem number 3. That is a 10-meter high cylinder with a cross-sectional area of 0.2 meter square, has a massless piston at the bottom with water at 20 degrees centigrade on top of it, as shown in the figure below. Air at 300 Kelvin with a volume of 0.3 meter cube under the piston is heated so that the piston moves up, spilling the water out over the side. Find the total heat transfer to the air when all the water has been pushed out. So in this, what is given? A 10-meter height cylinder. The height of the cylinder is given 10 meter with a cross-sectional area of 0.1 meter square. Has a massless piston. The piston do not have any mass. At the bottom with water at 20 degrees centigrade on top of it, as shown in the figure below. Air at 300 Kelvin with a volume of 0.3 meter cube under the piston is heated so that the piston moves up, spilling the water out over the side. Find the total heat transfer to the air when all the water has been pushed out. So here schematic is shown here. So this is the reference one figure, piston, cylinder, arrangement of the problem. So here we have to see that we have to draw the piston and the cylinder. This is the piston, this is the cylinder, this one, and here is the piston. So this is the here piston, above the piston we have the water, and this water temperature is atmospheric 20 degrees centigrade, and above that we have the atmospheric P naught is equal to atmospheric pressure. Inside we have, this is the system here, and the system is here air. So we have to find out the height is here h, and this total height from here to here. So this one is h minus h. This is h1, so h minus h, capital H minus h. So here given the height of this cylinder is 10 meter, area is given 0.1 meter square, air is given as a system, state point T1 is equal to 300 Kelvin, V1 is equal to 0.3 meter cube. So what is the P1? So we know that if we take a free body diagram of the piston, this is the P1, this is the P naught, and plus here water. Water is water pressure. This water pressure is H1 rho W by G. So this P1 is equal to P naught plus rho H1 rho W into G. So this is P naught H1 by V, because what happened here, rho is equal to 1 by V, specific volume. So P1 is equal to P naught plus H1 by V into Z. So we can see here that this V is equal to Vf at 20 degrees centigrade. So at 20 degrees centigrade we will find out how much is the Vf and put this value of Vf. H1 we have got it, G we know, P naught we know. So we will get the P1. How much pressure exerted by the air on the piston is 169.84 kilopascal. So this much pressure, this pressure is exerted on the piston by the air. So this much, this is pressure, it is 169.84 kilopascal. This much pressure is exerted here by this air on this piston. Now here P2 is equal to P naught is equal to P atmosphere, it is given, and this P atmosphere is 101.325 kilopascal. The V2 we know that it is H into area. H is equal to 10 meter and area is equal to 0.1 meter cube. So it will be 1 meter cube. So volume of V2 is given as a 1 meter cube. So if we draw the PV diagram, you see here, from here it is 1, and from 1 it will, here is a V1 and here is the V2, and this is the position of the 2. So here due to this spring, the pressure varies linearly with the height. So applying the first law of thermodynamics, Q12 is equal to M U2 minus E1 plus W12. So U2 minus V1, we can write that CV naught T2 minus T1 if temperature is not very large. So in that time, U2 minus U1 we can find out by this method. So here Q12 is equal to M U2 minus U1 plus W12. So here we can see that P1 V1 by T1 is equal to P2 V2 by T2. So U2 minus U1 is equal to CV naught T2 minus T1. So here, from here we can get the temperature T2. So Q12, if this we get this, we will put here this value of T2 from here, and then we will get the heat transfer. Q12 is equal to 220.7 kilojoule. So this much heat transfer is taking place. Q12 is equal to 220.7 kilojoule. We have worked out various problems related to the first law of thermodynamics with control mass systems. So here these are the references which I have taken. That is Yunus Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw Hill's 7th edition 2011, http www.youtube. This is the NPTEL lecture from Professor Suman, IIT Kharagpur. And any questions you are welcome to ask. My email is given as a ydwivedi@gmail.com. I also request to like and subscribe this channel. Give the comment in the comment box, and I hope you have learned very well. In next class, I am going to discuss about first law of thermodynamics for control volume system. In that, I am going to discuss about Reynolds transport theorem, which converts the control volume to control mass and vice versa. So that will be used for the fluid mechanics problem, how the work done and the first law of thermodynamics is used for the fluid mechanics. There I will be discussing these all issues. Thank you very much for the joining. Please be tuned for my next lecture, and that will be useful for the fluid mechanics issues. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.